American factories produce billions of rounds each year, and 308 Winchester still vanishes from shelves every time demand surges. Since its 1952 introduction, this cartridge has served overlapping civilian and military markets, building a demand base that no production schedule has permanently satisfied. The common assumption is that factories just need to make more. What's actually preventing them is a structural problem most shooters have never seen. This commercial release drew directly from the military's T-65 experimental program, a post-World War II project aimed at modernizing small arms. By shortening the service standard .30-06 Springfield casing, designers at Winchester engineered a cartridge that delivered comparable ballistics from a much more compact frame. This development yielded what became known as short-action efficiency, a design choice that allowed for lighter rifles with stiffer, more accurate receivers and faster cycling. Winchester capitalized on this physical layout by chambering it in their Model 70 and Model 88 rifles. Rather than relying on marketing claims, the round established its dominance on pure mechanical utility, proving that substantial power could be packaged into a highly agile rifle platform. In 1954, the NATO Committee on Small Arms formalized this physical layout by adopting the design as the 7.62 by 51 mm NATO cartridge under STANAG 2319. This standardization bound allied nations, including the United States, Great Britain, Canada, and West Germany, to a single interchangeable rifle and machine gun round. The United States military adopted this standard for the M14 rifle in June 1954, while European partners fielded it in the FNFL. Because the civilian .308 Winchester shared identical external dimensions with the new treaty cartridge, a permanent link formed between military supply chains and commercial production. This dual market adoption meant that tooling, brass, and ballistic research benefited both sectors from the beginning, securing the cartridge's multi-generational staying power. Modern manufacturing plants run on strict physical limitations. A state-of-the-art ammunition loading station can feed over 1,400 rounds of .308 Winchester every minute, managing case filling and primer setting in a single mechanical cycle. When a major domestic facility runs 70 of these high-speed machines in parallel, theoretical output climbs to millions of cartridges daily. Yet, this maximum rate represents a theoretical ceiling. Real-world throughput remains bound by finite factory capacity and the physics of metalworking. Ammunition lines must regularly reconfigure to support different product offerings. When a plant shifts production from high-volume full metal jacket to specialized hunting or match-grade ammunition, the entire line stops. These mechanical changeovers require 4 to 8 hours of planned downtime, plus another 2 hours for calibration and testing. For dedicated military lines, a physical caliber swap is even more disruptive, often taking 24 to 48 hours to rebuild and requalify the tooling under strict safety protocols. Every hour spent adjusting dies and feed trays is an hour of lost production, proving that factory output cannot instantly scale to meet volatile market demand. Expanding a modern ammunition plant to meet sustained demand is a long-term commitment. Installing a single high-speed loading line requires between $10 and $30 million in capital expenditure, while a full-scale factory expansion can easily exceed $200 million. Even with funding secured, the physical timeline for sourcing heavy machinery, preparing specialized facilities, and installing tooling ranges from 24 to 36 months. But purchasing machinery is only the first obstacle. A new production line remains completely inactive without qualified staff. Operating these complex high-pressure systems requires specialized CNC machinists, precision toolmakers, and safety-certified technicians who can manage tight chemical and physical tolerances. Manufacturers face a nationwide shortage of these skilled industrial workers, with vacancy rates across heavy manufacturing averaging 20 to 30%. This labor gap adds another 6 to 12 months of recruiting and rigorous safety training before a single new cartridge can roll off the line. This output rigidity stems directly from the realities of a slow, capital-intensive industrial process. Even when machines are staffed and running, factory floor logistics prevent a simple make-more approach. Centerfire rifle cartridges, like the .308 Winchester, operate under immense mechanical stress, containing SAAMI, maximum average pressures of up to 62,000 pounds per square inch. To guarantee safety, automated testing stations continuously monitor cartridge headspace within a tight window of 1.5377 to 1.5477 inches, alongside overall case length and projectile seating depth. These technical demands force manufacturers to separate high-volume production from specialty runs. Standard full metal jacket rounds can feed continuously through automated inspection bays, but match-grade ammunition requires tighter tolerances, aiming for a muzzle velocity variance of under 1%. Achieving this consistency requires slow, laser-based dimensional audits and manual sampling. Consequently, match-grade assembly lines run at approximately 70% of standard capacity. When demand spikes, factories cannot simply run all products at maximum speed. They must prioritize high-volume military and bulk civilian runs over precision hunting and target loads, leaving specialty shelves empty, even as the factory floor operates at peak capacity. The supply shortfall is not a single, isolated event, but a repeating pattern driven by predictable consumer cycles. Every year, market demand surges in distinct, overlapping waves. The first wave begins in late summer, as millions of hunters prepare for the autumn deer and elk seasons, buying up premium soft point and partition loads. Before this seasonal run fully clears, a second wave of demand hits from long-range precision competitors and tactical training schools, whose high-volume target shooting consumes millions of full metal jacket and match-grade rounds year-round. When these commercial surges collide with rigid manufacturing limits, the pressure shifts entirely to upstream chemical and metallurgical supply chains. Finished ammunition production depends on a continuous flow of specialized raw materials. Domestic ammunition plants do not manufacture all components in-house. They rely on a narrow network of specialized chemical suppliers for nitrocellulose-based propellants and copper alloys for brass casing production. Market indicators show that global industrial demand for copper and zinc often drives up raw material costs, while propellant manufacturers prioritize Defense Department orders over commercial contracts. A shortage in any single component, whether a specific chemical stabilizer or a run of percussion primers, creates a severe bottleneck. Because factories operate with minimal raw material stockpiles, even a temporary disruption at a chemical supplier halts the assembly lines, turning a brief surge in consumer buying into a prolonged supply deficit. This supply chain lag registers at the retail level long before industry analysts publish formal reports. When a customer encounters empty pegboards at a local gun shop, the situation reflects immediate local inventory exhaustion, rather than a systemic collapse of national manufacturing. To evaluate these conditions objectively, analysts test claims of a permanent shortage against empirical shipping and customs data. This standard separates unverified speculation from confirmed evidence. While internet forums often declare a permanent manufacturing deficit, retail point-of-sale data and distributor logs reveal a different reality. The factories are entirely capable of production, but price fluctuations reflect real-time inventory tension and deliberate machinery prioritization. During demand surges, manufacturers prioritize high-volume military contracts and bulk full metal jacket packaging. This temporary allocation leaves specialized hunting and precision match lines idle, causing niche products to vanish from shelves. The physical stock is missing locally, but the factories remain active. By tracking vessel manifests and producer price indexes, distributors confirm that raw material throughput persists, demonstrating that temporary shelf absence is a distribution bottleneck rather than a permanent structural failure. Today, empty shelves reflect physical limits, not permanent scarcity. Modern supply chains cannot instantly bend to sudden market surges. Until manufacturing infrastructure evolves, this delicate balance remains. Share your thoughts on these supply chain challenges below.